Okay, great. So, moving forward here. So today we've already talked about a number of interesting feed-forward networks that kind of fit within this kind of multi-layer perceptron, and then we did talked about some bio-inspired examples of where kind of one of the most well-known version, the convolutional neural network or the CNN or the ConvNet comes from, is sort of thinking about these kind of bio-inspired cases about how the visual system routes information from something like a layer to another layer in the vertebrate brain. But then we'd also talked about in the insect brain how there was a bunch of potential there for interesting structures that we can get out of that aren't currently, directly being exploited, but there's promising connections in that. It looks like the pipelines we already have with, say, feature extraction and encoding and decoding already kind of look like these things that have converged on similar structures and suggest that maybe there's more insights we can take from that. So with that in mind, we're going to then talk about a little more complex neural networks that are in use, and then bubble up and then how to train those neural networks, and then finish on some neural networks that are more exotic, but still being used, but get kind of closer to what I view as kind of like the complexity we see in these like biological networks. So that's kind of where we're going from here. And so let's keep things simple, but where I'm going to add a little bit of complexity at the neuron level, where we are going to consider neurons that can map from inputs at previous steps of time. And so before, we viewed a neuron as just basically a generalized linear model. And so you have a bunch of inputs and a bunch of outputs, and the output is sort of just a mathematical expression of the inputs. And so it is an expression capturing a relationship. How do these predictors relate to this response variable? And it sort of happens at an instant of time. We don't think about time passing in this calculation, but you can imagine that we could add a time delay where the output was actually a version of the previous inputs. And so this is related to, there's a group of networks that I'm not going to go into great detail in, but this is certainly related to the discussion today of time delayed neural networks, which allow you to form things like convolutional neural nets or feed-forward perceptrons, where each layer represents a different time delay and, say, an acoustic signal. And so that's kind of a larger group of neural networks that, if you're interested in looking into, you can sort of Google for those. But but if we focus in on an individual neuron, then you can imagine that we could have, say, a network like the one, let's say let's say I have an input coming in, X, and it goes into a neuron that I might call H1, and then that goes into another neuron that I'll call H2, and then that goes to some output that I'll call Y, and then that produces a signal output Y. So X goes into this group and Y comes out. And I'll write how these things relate to each other here in a second. But I'm going to then also create a link that skips this this middle neuron and jumps directly to this output neuron. And I am going to say that the mapping here is that the Y signal at the next time step, let's say, is equal to, and I'll say it's a 1 if the difference between the output of neuron H1 at time step K and the output of neuron H2 at time step K is equal to 0. And then it is a 0 otherwise. And so the key difference here is that I'm now saying that you could potentially have neurons that that depend upon the values previous values of old neurons. So we are actually adding in some element of delay in the execution here. And that idea that we can have this delay, so in this case, so in a time delayed neural network, this is, you can think of this as a more kind of analog delay, where you have layers that actually represent information at particular time, like this is 3 seconds back, and this is 2 seconds back, and this is 1.5 seconds back. And I can combine those different delays like you would if you were doing signal processing in physical space. There's this thing called a delay line. And a delay line basically says that if you instead of viewing a wire as a lumped element where the signal is the same all along the wire, you can actually view the wire as a delayed, a continuously delayed version of a signal, because the signal has to propagate down the wire. So where you tap out on the wire, this is a so-called delay line, gives you different views of that signal from different times back. And this is also why if you're writing a differential equation and you add some version of a time delay, then a time delayed differential equation, or a DDE, a delayed differential equation, is so-called an infinite dimensional system, because it's kind of like in this delay line, you can tap anywhere in there and you have to keep track of the entire continuum of delays. And so a time delayed neural network is kind of like a neural network version of the so-called delay line, but I'm thinking even simpler than that here. So where I'm just saying that the next output is some function of the previous outputs. And having this separation in time, so you can think of this as a synchronous system. So at every clock cycle, I sample whatever's going on now and I shuttle the stuff that was going on forward in time. And so having that allows us to play with these neural networks the same way, if you remember from your computer architecture courses, you might remember going from combinatorial logic to sequential logic. And so once you had these flip-flops and things like that, that allowed you to create feedback loops. And these feedback loops allowed you to make use of memory in interesting different ways. And that's what we're going to do with these neural networks here, is saying what happens if we actually can embrace delay? What sort of new network structures can we form? And the first ones are just new feed-forward structures like this one. So if I were to, so this feed-forward system here, first, are there any questions about this representation? So I've kind of drawn this kind of simplified signal flow diagram up here. And so hopefully that kind of makes sense here, that and so in this case, I'm just saying that for this particular network, I'm just making Y 1 or 0. Y basically is a detector. And in the two Ys here, this is a question of why are there two Ys, a Y inside the neuron and a Y outside. And this, I'm just kind of using different classes here. I'm viewing the lines as signals and these as neurons. And so this neuron is named Y, and the neuron's output I've also named Y. But you can think of the line as kind of a different than the circles. And so we've got neurons and we've got signals. Signals come out of neurons, signals go into neurons. So I can name both of them, and these two happen to have the same name. So I'm naming the neuron for the same name of its output signal. So likewise, I could also put an H2 here, and I could put an H1 here. And I could say, if I want to index these whole things, I could say, well, if this is Y of K, then maybe this signal going into Y is H2 of K minus 1. And maybe this signal down here going into Y is H1 of K minus 1. And so back here, I could say this is H1 of maybe K minus 1. And so I could name these things in terms of how they're related. And so this X that I'm seeing back here might be X of K minus 2. So it might be that in order to get through each neuron, you have to pay a delay. And so so that's like how I could name all of these different things. So I'm just differentiating between the name of the neuron and the signal. So any other questions about this representation? Okay. Good, good. All right. Okay, so if I were to then think about what these signals might look like over time, then this X signal, X of K, and this is over all K, I could imagine that it takes some, I'm going to just say it takes values of 0 and 1. And so the X signal takes values of 0 and 1. So I'm going to say, what if it's initially 1? So I'll just draw little Kronecker deltas here. And then at some time in the future, so each one of these things is one time step. So maybe I'll draw a little 1 here just for scale. And then so maybe I go through 3 that are 0, and then it jumps up again and it goes to 1, then 1, and then 1, and then back down to 0. And then I see a question here. From what you explained, the signal from H2 neuron would be H2K and not H2K minus 1, i.e. if it takes one time unit to come out of a neuron. The signal from H2, well, I guess I'm sort of referencing everything to the reference frame of Y. And so I guess it was my perspective when I kind of wrote this, and maybe I just haven't thought this through because my brain slows down when I lecture. But the thought here was that if I'm referenced to the output, then this signal back here, reference to the output, is well. So I guess it might be an abusive notation here. So I guess I'm just trying to say that the indices that I'm putting in here are kind of like the information that could be available in this calculation. Okay. But yes, I take your point that yes, that I could have put K's throughout all of here, but I guess I was just trying to condense everything by just kind of showing what's available right now at this calculation out here. All right, good. So so I've got my X signal, and that's what it is. And then I wanted to see, like, what does my Y signal look like? And so if I were to draw my Y signal underneath it here, then likewise, I'm going to say it takes either a 0 and a 1. And so basically, I'm saying that Y is a sameness detector of H1 and H2. And so if or I guess what I could possibly, maybe what I should do here is if I were to rewrite this Y from up here as in terms of X, then I could say it's a 1 if X K minus 1 minus X K minus 2 is equal to 0, and a 0 otherwise. And so this says that Y detects sameness of X at time K minus 1 and X at time K minus 2. And so with that in mind, then if I were to look at these two here, then these are not the same. So that tells me that my output here, maybe I'll draw this in a different color, that because these two are not the same, then that output is going to be 0. It's going to be different. And but then these outputs here are the same. And so because of that, then this output will be a 1. And then these outputs again are the same. So again, I get a 1 again. Then I detect a difference, and then 2 more same on the output. And so that's what kind of this sameness detector looks like. And so the reason I'm going through all of this is by creating long range connections between layers. And so if we were to think of this H1 as a layer and H2 as a layer and Y as another layer, this output layer, then this connection between, skipping a layer provides Y the ability to detect patterns in more than one layer. It allows it to detect patterns across time. So connecting across different layers allows for the detection of patterns. And so so I guess I could write that, this is, long range connections detect patterns, or one way to detect patterns. And so you could imagine that I could have just kept at the input. I could have said, I've got my input at time, or I've got my X input. I could have augmented that input with delayed versions of X, providing like, instead of providing all of my X's, providing like an array of past X's all at once, or this kind of volume of information about X. And then I could just have this feed forward network that is sort of like a multi-layer perceptron, where every layer only talks to the layer ahead of it. And if I were to do that, then carrying this historical information along, this big bulky historical information, then I could detect patterns. But this is like a more succinct way to do that, because now I can actually have the layers talking to each other, and that allows me to feed in a relatively simple input and detect patterns. And the patterns I'm detecting, the signature of those patterns are in the connection structure themselves. So this structure is actually like, remember I talked about a single neuron is a generalized linear model, or a single neuron is a classifier where the weights of that single neuron are somehow a prototype of the individual member of that class. Well, now the connection pattern has been lifted up as being part of that prototype. And so not only are the weights important, but so is the sort of connection pattern. And if those of you who've ever taken a signal processing class might be familiar with the so-called finite impulse response filters, otherwise known as FIR filters. And they're called that because if you give them an impulse, which is just a mechanical engineer's way of saying if you whack them hard. So or maybe it's an electrical engineer's way of saying what a mechanical engineer would say is you whack it hard. So if you hit the input with a spike, a single spike, you can watch what the output is going to be. And it turns out that if the pattern that comes out, like if you hit a bell and you listen to the way it rings, there's a way to reconstruct the way in which it will ring if you give it an input more complicated than a single pulse of a hammer. And so similarly in a room, if you make a loud chirp, you can listen to the way in which that chirp reverberates throughout I don't actually chirp as a technical term, so I don't mean a loud chirp, a loud pop. So if you make a loud pop in a room, and then you can listen to how that echo happens around, then the delay in which that echo takes to dissipate actually tells you how, if you were to speak in the room, how the room would distort the way you sound. And so you get that all from the so-called finite impulse response. And it all comes from this connection topology that's in the network, or the physical constraints of the room. So that's what we're effectively doing, is we're setting up echoes around a network. And that will come back, we'll land on this sort of echo state network later, that kind of takes this to the extreme. But we are setting up a connection topology which gives us more ways to represent patterns in time, not just patterns in space. So that's the simplest way we can do it, with just a feed forward way, where we're going to take layers and feed them to layers that are long ways away. And the longer you get away, then the longer the patterns you can discriminate against. So then the question is, what other sorts of structures can we build? If we want to detect very complicated patterns that maybe exist over very, very long time spans, do we have to generate very, very, very deep and long neural networks? Or is there a way for us to build smaller networks that can still detect patterns that have very long time scales? So I see a question here: how are the two connections to Y can interact together if they have different outputs? So I'm not sure I understand the question, so feel free to clarify, but these two inputs to Y, one of them comes from a node, which is delayed more than the previous node. And so these two different delays are being fed into the same neuron. And so then that neuron can then put different weights. And so in this case, the weights here, effectively I'm putting a positive one and a negative one on these weights. And so and then I've given it an activation function, which basically gets activated when the sum is equal to 0. And so these two things aren't interacting, but they're being combined, and that's what gives us the output. Okay, good. All right, so let's think about then other ways that we can combine things. And so we could say, well, why are we limited and just feed forward? You know, is there some advantage to actually allowing signals to propagate backwards? And so you could imagine that I could take my same input. So let's say my goal is an input, my input signal X, and my output, this is my goal here, and my output Y is going to be, they'll say, should detect if X is equal to 1 ever in the past. I see a question here. That would be, so I missed what this is responding to, this question. I see in the chat, that would be like reconstructing T-1 based on T. And so again, I don't know what that was responding to, but the reconstructing is the backward connection. Well, we'll see how what I mean by backward connections. Yeah, let's just see how this example turns out. So I'm trying to generate this here where the ever, so this is almost, you know, so this could potentially, for those of you in software verification or whatever, you could imagine this also generalizing to temporal logic. So you could say, how do I detect that something that ever happened in the past? I don't know where it happened in the past, but ever. So that sounds, in this case, this is a predicate, which is, you know, over, you know, infinite time horizon. And so if I just had feed forward in my tool set, now that was it, then this would be impossible for me to guarantee, because I'd have to make a really, 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 really long neural network. And it would only have access to whatever delayed version of the signal was stuck in that neural network. And once, if the event happened farther back than I could remember in the neural network, then the output would go low. And so I really need some real notion of state inside my neural network, where my neural network now has the ability to remember things farther than the confined structure of the neural network itself. And so one way we can do that is by introducing recurrency. And so the idea would be that if I have a signal X and I've got some neuron Y, again, that neuron has some output, but I'm also going to allow Y to feed back on itself, so that the inputs of Y is a combination of X and the previous Y. So I might say then that Y of K plus 1 is equal to 1 if, and I will then set up this linear combination, if YK plus XK, let me think this through. I think I need XK plus 1 is greater than 0. And off the top of my head, I feel good about K plus 1 here, but the analysis isn't going to change much if this was a K. So, and then a 0 otherwise. So this simple linear combination that I have put here and activation function, I could implement with the neurons that I've seen, maybe dealing with this, you know, making sure I've got some sort of delay element for memory. And so then what I mean by the linear combination here is that if you view yk and xk plus 1 as these two inputs coming in, then this linear combination is, you know, that in our neurons, like our prototypical neuron that we've had in the previous lectures, then we had an activation function that was fed by a sum. And then that sum was a sum of weighted versions of the inputs. And so in this case, the weight that I'm putting on the y input is a weight. I'll say weight of y is equal to 1. And here the weight of x is equal to 1. Just like in the previous case, the weight here is, so I'll say the weight of this one is equal to 1, where the weight here is equal to -1. And then I'm summing those things together to get my output, and then I'm running that through an activation function. So the same thing here, where now I've weighted these by they've both been weighted by the identity by 1, and then I've put them through an activation function, which only activates when their sum is greater than 0. So this is something that's implementable in a neuron. How will the math for, yes, we'll get, that's backpropagation is our next, you know, so how the heck do we train these things? That's our next page here. And what does it mean to have a sum greater than 0? That's what we're going to see. So we're just saying that the activation function is on so long as this is greater than 0. And so now we can say, well, how can I show that this does what my goal was? So my goal was to make it so that the output is high so long as the input was high once in the past. And so and then I now have to have an initial condition where y at time 0 is equal to 0. And so now if I have an input x of k, and I've got my output y of k, if my input is 0 for a little while, and then it eventually becomes 1, then my output, the way I've written these delays right here, is going to be, and let's say the input then becomes 0 again, then I know that when x became high, then we know that y will be able to become high, but then x goes low. But now that y, because the previous version of y was high, then the next version of y will stay high. And so y will now be 1. So y for all k, you know, greater than whatever that, for all k sufficiently large, y is going to be equal to 1. And so x only had to be 1 once, and then now the y is going to be equal to 1. So we have now given this is a so-called infinite impulse response, or IIR filter, which just means that the system can is self-sensitive, so it can kind of self-amplify, so that when you ring the bell's own ringing keeps it ringing in the future. And that means that the bell stores a state of the past of the input. And so this allows for a better use of storage. And so this helps us detect much, much longer range patterns in a much shorter space. So that's really what the point of recurrency is it's so-called recurrent neural networks or RNNs detect patterns and they store memory for a long time. So that really is the main function of these, so so the 2 points I'm trying to say here is by, although it's convenient to have independent layers and these kind of like bipartite or multipartite networks, creating jumps across layers helps you encode patterns in time, or perhaps in space, depending on like what domain you're operating over. And then recurrency allows you to create even longer timescale variations. The downside is that the recurrency gives your systems more of internal dynamics that can actually corrupt your outputs. And so in the case of FIR filters and IIR filters in signal processing, then it turns out that things that are designed to have this finite response end up actually having less corruption of signals that are supposed to pass through them, but things that have an infinite response tend to add more corruption. And so similarly speaking, like this neural network that I just drew here, even my input was on once and now the output is high forever. And so it kind of has a mind of its own. And so there's no way that I can get the output to go back low again the way this is designed. And so as we'll see, I'll talk about a particular type of very successful recurrent neural network that a lot of mathematicians worry about, because it has the ability that it sort of has a mind of its own, has very chaotic dynamics, and that gives people the worry that that it will end up producing results that are kind of nonsensical and become decoupled from the input. And so so generic RNNs then, so a generic RNN topology, you can think as truly fully connected. And so you could imagine just a mess of you know, you could imagine for every neuron, they all could connect to each other in any direction, and even self loops. So you know, it's you could say it's sort of the unconstrained topology. And it seems like, and there's ways in which we can simplify this so that we don't have to draw this. We can just write this as a linear system. At least when we have, if we have linear activation, at least up to a point, we can think about this as saying that, okay, well, what if the I've got my recurrent neural network, I'm just going to call H some vector output, and it has a matrix operating on itself called A, and it has some matrix producing an output called Y, and it has a vector valued input called X, and there is some relationship B relating X to H and C relating H to Y. And so we end up getting something out that where the system can be written as H at the next time step is just a transformation of H at the previous time step plus a transformation of X at the previous time step. And our output Y at the next time step might just be equal to H, we'll say, at the previous time step. And so this is a, you know, compact version of the RNN topology. So, you know, it really captures this idea that all of these hidden layers are really an internal state of the system. So those latent variables now have latent dynamics. And so as a dynamical systems person, you don't have to worry about, are those latent dynamics stable? So if I turn off the input, will the internal dynamics also die down and all that? And so those are all issues that become very difficult to answer in modern recurrent neural networks. But if you can, say, find a way to represent your recurrent neural network in a linear way like this, we do have tools for understanding that here. So that's, you know, part of, there's a research direction in sort of saying, you know, how much can we capture in modern recurrent neural networks in more in less sophisticated mathematical forms that we can analyze. And it may seem more natural. Sure, you can. This is kind of the difference between a mealy output and a more output. And so, if you like, yeah, you can get rid of this extra output layer that I'm implying is there and change this k to a k+1. That's fine. But just sort of saying that this is one compact mathematical way to potentially write a connection topology, supposing that you don't have a lot of nonlinear activation. All right, but so that's just kind of like our intro to RNNs. And so if once we have these RNNs, then the question that's been already brought up is how to train RNNs. Because we said that one of the really nice things about the totally feed-forward ones is they had this beautiful structure in backpropagation where I basically take an error function or an error measurement, and then I push it into training the back layer, and then I can propagate that error back, and I only have to worry about gradients at each layer. And then once I've kind of moved those gradients, then I can propagate the input forward again and go back and forth over this entire neural network. And so how do we do this same thing when there's no obvious striations in our network? And so the generalization of backpropagation is something called backpropagation through time, or BPTT. And we're basically going to unfold a neural network in time and then pretend like the time unfolded neural network is a feed-forward neural network. So this, so I could say, well, I guess I'll just write this is backpropagation through time, or BPTT. And so the idea is that I'm going to unfold RNN execution through time. So as an example, I've got this A matrix up here, and that goes in to my internal state variable h of k-1. And that is also got inputs coming into it. So you've got x of k-1 coming in, and you've got the y of k-1 coming out. And then you can imagine then that internal state gets propagated to the next step. And so we've got h of k. And then likewise, it's going to have its y and its x connected to it. And then that gets propagated to the next time step, h of k+1. And then likewise, it's got its connections y, let's say at k+1, and x at k+1, and so on and so forth. And so in this representation, there are no loops. So by iterating over time, we can create an expanded neural network where we have taken what was a bird's nest of connections, and we have then put them into a directed acyclic graph over time, where now it's almost like we've got a feed-forward neural network that is so that we're able now to sort of then use our intuition from backpropagation to push back through it, but we're now pushing back through time, although it feels like we're pushing back through space. So, and so I won't go into details with this, but I just wanted to motivate the idea, and if you'd like, I can kind of leave as an exercise. You can take the same exercise that we did with backpropagation on a multi-layer perceptron and apply it to this framework where you're thinking about the neural network moving back through time. and you get the same type of idea where you can separate out concerns, where you can train all of your weights at one time step, and then once you've trained all of them, you can push that back to the previous time step, and so on and so forth. Sure. Yes, I'm behind in getting the reading for this one, partly because I have to find it. So again, this is just all just kind of from memory, and so finding good readings. I'm sure I could probably find a couple of chapters that I can copy and put out there that will cover most of this stuff. And so it's on my to-do list, and I apologize for not having it ready right now. But these are, you know, decent keywords that I definitely recommend. Like, these are like standard terms, backpropagation through time, and so on. And so in the meanwhile, then definitely, I just want to get you at least familiar with these ideas, that because I bump into a lot of people that I think are introduced to neural networks, and they'll say something to me like, oh, recurrent networks are great, but you can't use backpropagation with them. And so somehow in our education on recurrent neural networks for data science people, at least kind of at the master's level, somehow it's getting lost. And so the big reason I put this into this lecture when I put it here was mainly to give exposure that, by the way, even in recurrent neural networks, you can actually still use backpropagation. And in fact, if you use, you know, things like TensorFlow, for example, if you build a recurrent neural network, it will most likely just be using backpropagation to train that thing. So so there's a question. I didn't quite how we made this linear in time space. So this is a simplification. So this is a linear simplification that applies, let's say, for linear activation functions. So if I have a recurrent neural network with linear activation functions, then I can write that neural network in this form. In general, if you have nonlinear activation functions, then you may not have such a concise, closed form mathematical expression for that. And so I was writing it in this form to help motivate the backpropagation through time, so that it was easier for me to write an operator that allows me to operate across time. But in general, to sort of, this operator here can be much more complicated. But that's why I was saying that an active area of research is to say, can we find, say, linear recurrent neural networks that do all of the things that the fancy nonlinear recurrent neural networks do? Because if we can, then we actually have a bunch of tools to be able to analyze this system, to be able to say things like, is the recurrent neural network stable, et cetera, et cetera. So for now, I was just writing in this compact form so that I could then write this in a compact form. But in general, a recurrent neural network won't be something that could be easily represented in terms of a linear model. Okay. All right, so are there more questions about this kind of idea, this rough idea of that we can use backpropagation, where we unroll a neural network in time and effectively turn it into a virtual feed-forward neural network that can be trained just like a multi-layer perceptron? And that's effectively what's being done. If you go into TensorFlow and you say, train this recurrent neural network, that's what it's doing behind the scenes, is unrolling your recurrent neural network in time. Computationally expensive, but hopefully your recurrent neural network might be a little smaller than your multi-layer perceptron. And so maybe the unrolled version will actually be of similar complexity as a more complex feed-forward version that doesn't have recurrency. Okay, if we want to unfold an RNN having nonlinear activation functions, we need the RNN with, well, okay, so this, again, I was just sort of showing it in this linear perspective to make this easier. You could you can unroll nonlinear activation functions also back through time, but I was trying to make it clear that how this operator works, that you have an internal state that gets operated on by a matrix, and that makes it sort of easy for me to write it this way. But if you have a nonlinear So I could have turned each one of these A's from a matrix into a giant multivariable nonlinear function of the internal state of the network. And then that would be the operator pushing this thing through time. And so you certainly can do that, but it was just simpler for me to write it this way, is that I've got an internal state that I multiply by an operator to give me the next internal state, and that's how I roll it back. But you can even do this with nonlinear activation functions too. Again, I was just, as a simplification, saying, assume that we have linear activation functions, then we can write it like this. We can take this mess, write it like this, and then once it's in this form, then it's easy for me to depict backpropagation through time. But you can apply backpropagation through time to a generic recurrent neural network, even with nonlinear activation functions. And if, for those of you that are kind of physics minded, you can think of this operator as a kind of Hamiltonian that is moving you through time, and you're just backpropagating over the Hamiltonian. So for those of you more mechanically inclined, that's another option to think about this. All right, so so no loops, and so use backpropagation. All right, so this works great if you've got a recurrent neural network that is small. If you do get into this rat's nest of giant numbers of neurons and giant numbers of connections, then this won't necessarily be a computationally friendly thing to do. Just like if the convolutional neural network is a regularization of the multi-layer perceptron. So the multi-layer perceptron says, well, we've got lots of layers, these pancakes that are sitting in parallel with each other, and each one of these pancakes connects to each other. And we're saying, well, with the convolutional neural network, we are going to make it so that you've got these tiny little flapjacks, and each one mapped to a bigger pancake that map to a gigantic flapjack, and that this coarsening over time means that we have less training to do, and it actually makes it easier to train. And so what can we do in the terms of recurrent neural networks? So, well, what people have done is they said, well, how can we come up with clever recurrent neural network structures that regularize this ugly rat's nest of neurons that are in a generic RNN that make it easier to train and maybe better performing? And so one that you've probably heard of, and so this is, I'm going to put under the topic of regularization of RNNs. And so under that topic, and so that's a fancy name for, I'll say, adding topological structure to neural networks. That's effectively what regularization does, is it reduces some of your design flexibility and hopefully improves the training performance then. And so, and again, a lot of you have probably heard of all this stuff before, but long, short-term memory, or LSTM, is a particular technique that has been very successful in producing these recurrent neural networks that have been relatively easy to train and relatively successful at prediction problems, for example. And so, and actually, what's interesting here is LSTMs are pretty old. I think some of the first references to LSTMs were, like early 1980s. But they kind of, as neural networks, kind of fell out of favor, but, they were kind of forgotten about for a while. Then they came back. And so the people then took this kind of ready-made technology off the shelf and applied it to, search engine queries and things like that. And it seems to work pretty well. And so it's really taken off again. And so the idea here is that an LSTM breaks, so keep in mind, I said a recurrent neural network effectively keeps an internal state. a hidden state, a latent dynamics, a latent state inside the neural network that is used for better processing, so you can get better prediction of patterns over long periods of time. And so long short-term memory is motivated by this idea that maybe sometimes and thanks for, there's some people that were adding references in the chats. So the basic idea is that I need to potentially remember something from a long time ago, but I don't necessarily want to remember everything from a long time ago. So I might want to remember an important detail. So if I'm trying to predict the next word in a sentence, I might want to remember the context of the paragraph or the context of the chapter. But I don't necessarily need to have to remember every single word up to that sentence in the chapter. So I somehow might need to remember things locally. So I need to sort of keep in mind, like, you know, what's going on in the last couple of sentences and what's the bigger context. But then otherwise, I don't need, you know, so I don't need all of the other tiny little details. I need to forget some details and remember others. So we're going to break up the hidden state. So this was kind of this H vector. And you can think of this as the kind of memory to include and we can think of this as having a cell, we'll call it, that can store values for long periods of time. And then I also need, I'll call them gates to control access to that cell. And so you can think of this as I still keep my I still keep memory that of everything around me, but I have like a special latent variable that's off on the side. And that latent variable, my neural network can decide when it's time to update that neural network, that latent variable, and when it's time to and when it's when it's time to update it and when it's time to use it. So if we were to think of my internal memory, so if these are all of the kind of internal memory inside the neural network, then I can imagine creating a topology where I've got maybe some internal dynamics that are very similar to kind of like my standard neural network, but then also this special variable that is not always being updated and is not always being used. And so there's kind of the, you know, my inputs are coming in, my outputs are coming out, but then are these special connections between this special cell and the outputs and the input. And so I basically, under certain conditions, I will, and maybe I also have connections coming down. Oh, I guess I already drew that one. And so under certain conditions, I will reset my cell, my like long short-term memory. So it's short-term memory in that it's working memory, but it's longer in that it's harder to erase. And so it's harder to update. And so to give a more concrete example, like let's say I am predicting the next word in some text. And so, so let's say so this is like a nice NLP example. And so I would like to predict, you know, somebody has typed in, the boy called thee, and I don't know what they're going to type next, but I would like to predict what they are going to type next. Now, if I look at the boy called thee, those are kind of very local signals. And so you can think of these as in recent history, the boy called thee. This is what happened very, very recently. And there's a bunch of different things that could follow here. And, I know that there's a boy and I can look up on, different things that boys could do. I know that it's preceded by a thee, so it's an article, so I can think of parts of speech here. And there's just a bunch of different things that I could put in here. But if I zoom back and I think then of like, what's the context here? And if I can say, well, far earlier in the story, I know that there's some context that, let's say, there was a fire. And so if I know that earlier in the story, way earlier in the story, then the building, caught on fire, then suddenly I know, I know that the boy didn't just call anything. He didn't call, he didn't, call down to the candy store to see if they had a particular chocolate bar. He called the fire station. He called the police. It immediately limits things. But the context might be, and maybe it's not a fire. Maybe the boy instead, maybe we know that the boy was recently in his first breakup, in a relationship. And so, then, if this was, the context was after a breakup, then we know that he probably didn't call the fire station next. I mean, unless he was very destructive and, and set a fire or something like that. But the idea here is that the context greatly changes the prediction. But in order for us to keep track of the context, we don't have to keep track of every single word in the story. So this long short-term memory just gives us a little depot where suddenly the neural network still has to be smart enough to identify context, and it still has to then take that context and store it somewhere. But then once it's stored somewhere, if it leaves that context in there, then that context can shape the next predictions. And so that's what they mean by long short-term memory, is it's a special part of the internal state that is distinguished from the normal internal state. It's harder to change, but it is allowed to season the inferences being made in the rest of the neural network, but does periodically get updated as the neural network sees fit. So, and this has been, like I said, very successful in a wide range of pattern recognition problems. Yes, C is the long-term memory. So I'll call this the long short-term memory. So this is my vector C, which is the cell that I've put down below. So that here is the special cell, the long short-term memory. And you can train LSTM with backpropagation through time. And yeah, no one actually knows how to interpret how the heck LSTMs work. This is the narrative that we use to explain how they work. We say that this internal long short-term memory is keeping track of a kind of context, and that's helping the neural network. But without actually unpacking the neural network and studying the latent variables and seeing what's represented where, then we don't really know that there is a notion of context that's being stored in there. We just sort of, was the heuristic that was used when these things were built. They said, we're going to have a sort of ugly rat's nest of internal memory to keep track of local stuff that just happened in time. And we're going to then have a separate branch that is harder to update. And that's going to hopefully allow us to keep track of longer term relationships. But that if you actually train these things in your particular application, the neural network could be making use of that in other ways, or it could just be totally ignoring it. Who knows? Or it might just be filtering your data at a longer time scale. But at least the story is it keeps track of kind of a context. And the long is that it's has a longer time scale than that. So if I were to write here, I could say C has longer time scale or lifetime than H, but it's still short term in that you're not like writing out memory to disk. So it's still like working memory, but it's just a little more persistent than all of the other working memory in the neural network. And the algorithm designer doesn't know what hidden state represents. No, that's the, yeah, you just kind of, you give it the topological structure, and then you train your LSTM. And then hopefully your LSTM comes up with a cool internal representation of the patterns you're looking for. And then you can then unpack the LSTM and see how the weights are set. And then from those weights, you might be able to say that, oh, I see now, it's really paying attention to whenever I hear a dog bark, something fires and it's stored in memory, and it waits to hear another dog bark within a certain amount of time. And so then you could discover that actually it's looking for dog barks separated by, 5 seconds, but in the execution of a neural network, 5 seconds could be thousands of cycles. And so it's a way for it to store that relationship without having to store 1,000 cycles of memory. So it is, in theory, this is like this explainable AI, XAI, is that in theory, you can open up a neural network, probe it, and see what the heck's going on. But we still don't really have a good idea of how exactly to do that. But in principle, yeah. And if you can figure out an objective way to do that, people write papers on that. That would be an excellent papers to add to the papers that people are already writing on that. So I think I covered what the short is for. The short term is, both of these memories are short term, H and C, but this is longer. It's not long-term memory. Long-term memory is like writing something out to disk and making use of it. So this is just more persistent than the normal memory. So any other questions about, yeah, is this related to Bayesian priors? You can think of this, if you would like, you are free to think of this cell as kind of a prior that gets updated. It's like posterior passing. You update your posterior, and that ends up then becoming your new prior, and then that may improve your estimates over time. But the downside of that interpretation is it kind of suggests that we're doing online learning. And we are going to talk about online learning next lecture, but this is usually thought of as being trained all at once. But still, you've got plasticity here, so you can kind of think of like forming a representation. So I know there's Bayesian interpretations to everything, and so there's definitely a way to interpret this from a Bayes perspective. I kind of view Bayes as a lens on which you look at things to make sense of them, and if it does help you to make sense of this using a Bayes lens, I think that is a Bayesian lens. That is definitely a reasonable thing to do, but a priori, I can't say, that this is meant to be a prior or anything like that. All right, great. All right, so the last thing that I want to mention in the last 10 minutes here is a totally different way of thinking about recurrent neural networks. Here, we built a structure and we trained the whole structure. Now, I mentioned to you that, like, as we look into things like insect brains and such, and actually even the vertebrate brain, we see a number of connections that don't appear to be trained. They seem to be at developmental timescales. They end up being connected randomly, and then they're made use of. And so it's as if they stay random. And we don't know if the synapses are getting tuned, but for all intents and purposes, it looks like these are parts of the brain that do not have the same type of plasticity. They're like a rigid randomness. And so with that in mind, enters a different recurrent neural network structure, so called the reservoir. I'm going to call this reservoir computing or reservoir machines. Of which the most popular neural network in this class is the so-called echo state network, or ESN. Now, I'm not going into a great deal of detail here, but the motivation behind reservoir computing is that people looked at these recurrent neural networks and they said that RNNs are dynamic. So if you hit the input, if you twiddle the input of an RNN, then you get interesting patterns on the output and potentially even chaotic. And so maybe someday, if it comes up in questions, I can talk about, if for those of you who aren't familiar with the formal definition of chaos, we could talk about that. But for now, just imagine that I'm saying that there's internal dynamics are complex, and they have so there's cool patterns that just naturally play out over time series inside of a recurrent neural network. And so the thought was, let's think about a cup of water. So this is a cup of water. And that water cup has got, it sits there relatively still. Yeah, Jurassic Park. This is if you've seen Jurassic Park, you might see, you kind of know where I'm going with this. And so if you were to, let's say, vibrate the table, then you are going to create ripples in this cup of water. And those ripples will ripple even after the vibrations have stopped. And so the water, the surface of the water, becomes a time delayed version of vibrations at the table. And as long as you leave the same amount of water in that cup and don't change the shape of the cup, then there will be consistent patterns. And so these can be consistent water, I'll say H2O patterns. And so the thought was that maybe I don't care about what is forming those patterns, but maybe I can make use of this stretching out of an input over time, and I can just connect a neural network to the patterns that I get for free from the water. So you can imagine attaching some laser vibrometer to the surface of this water. So it hits the surface, maybe it reflects off, and it gets collected at some other area. And then I could tie that laser barometer to let's say, just a feed forward neural network. With some output over here. And then so I view this table as my input, and I view this coming out of the network as the output. And I actually view the water, the reservoir, as and the echoing that's going on throughout the water as a way in which I can represent information over time in a more spatially convenient way, so that a much simpler neural network can be used to actually solve the problem that I'm trying to solve. And in this case, I then only need to train this small neural network. Now, of course, using a glass of water for this is silly. Now, in principle, it turns out that DARPA now wants to actually put money into this sort of thing, because instead of a glass of water, you can actually have a soft material, let's say in a soft robot, and that soft material ripples the same way the water does. And so the Department of Defense is very interested in knowing, can we actually use the jiggles that are in soft robots as a reservoir on which you can do this expanded representation of signals? And so is there a one-to-one pattern? Well, we don't know. That's the whole point, is we don't know if there's a one-to-one pattern here between the inputs and the ripples here, but we sort of assume that there's probably not a lot of degeneracy in the ripples. In other words, we kind of assume that we probably are going to get more representational space at the surface of the water and not less. So we kind of take as an assumption that there probably is a one-to-one mapping, or you can view this almost as a hash function. So you can almost view this as a hash function that is somehow over time. So getting to the punchline here in the last minute that I have here, and I can maybe come back to this at the beginning of the next lecture, you can build a reservoir by creating a randomly weighted RNN. And so you have an input that comes in, and then you have a simple output, or I guess decoding layer that then goes to your output. And you can train this, but you do not train this. Now there are hyperparameters, but you don't actually worry about the individual weights. And so you might say, I want the network inside my randomly weighted recurrent neural network to have certain connectivity properties. So I want it to have one connected component, and I want the weights, you know, I've got a certain spectral properties of how these, the adjacency matrix of all these weights play out, and so on and so forth. But you don't actually train the individual weights. You just randomly instantiate the recurrent neural network, and that recurrent neural network becomes the stand-in for your glass of water. And then you just have a couple of weights to train in this output layer. And it ends up, what they've shown is that although there's even less analytical tractability in how the heck these things work, they are very simple and cheap to train, and they have pretty good performance at things like time series classification. So I can pick up here because we're at time. I don't want to leave things too far. I will stick around here in this room until 4:30, and then I'll switch to my office hours room. Anybody that wants to pop off can feel free to pop off. Otherwise, I'm happy to take questions for those that want to hang around, and then I'll record the questions and post the video with the questions. So are there any questions about this reservoir network idea? All right. Yeah, you can think of these as, there certainly are relationships between this and things like compressed sensing. So I mean, it's a kind of a convergence of ideas. This idea that random filtering produces interesting perspectives on data that are more useful than the data itself. Why do we not train the RNN? Well, and it turns out if you did train the RNN, you might actually do worse. Because you might end up training it into a local optima, or you might end up getting, you know, not converging on a local optima and getting stuck out in the weeds somewhere in somehow biasing the way in which you're filtering the input. The big reason not to train it is that you're trying to make this time series classification faster to train. And so the idea is that rather than training a gazillion amount of neurons, I can train a very thin layer of neurons, and I can train hopefully much faster, or at least use a lot less effort in my training and get a very similar performance out. Are there any application examples for needing to use an RNN? It seems very complicated to work with, so why would you want to work with that? So if you're just doing static classification, so I look at this page and I detect letters, you don't need to use a recurrent neural network for that. A recurrency is really needed when you need to predict things over time. So you need to predict what I'm going to write on the next page based on what I've written on the previous page and what I've written on the page before that. It ends up becoming economical to actually go the recurrent route. They seem complicated, but they are a more compact representation of patterns over time than than what you would need to do if you did a totally feed forward. Because in your feed forward case, it might need to be like a whole lot of layers. Whereas in recurrency, I can maybe have a couple of layers with recurrency and I still capture all these patterns. It is as if I drop my image pixels through a sieve of random patterns and study the dropped pixels on the ground to see what the original. Yeah, I would actually argue it's that you could almost even think of it as dropping it through multiple sieves, that each one are drawn randomly, and each one are at different heights, and then looking at the kind of family of patterns that you get on the ground. And from that family of patterns, knowing the sieves that you put them through, then it sort of tells you interesting things about the input. Again, this has got relationships to things like compressed sensing. So if, you might, for those of you who might be interested in the kind of signal processing versions of this, compressed sensing is definitely an area that is related, although I would say this is probably even more general than that. Can you talk on this simple output decoding layer to describe what the output will be? Or, we'll give a set. Does it describe what the output? So basically the output layer, now you could in principle also route the input layer to the output layer, but in the simplest form, you pick a set of neurons. They aren't all the neurons, but a small set of neurons, just like you pick a spot for your laser vibrometer. You pick a small set of neurons inside the randomly weighted recurrent neural network. And those become the inputs to this output layer. And then you train this layer based on, well, I mean, it's based on the ultimate input, but the only weights you have to tune are weights that are tied to the recurrent neural network. And so the recurrent neural network is just creating a stretched out image of your input. And then otherwise, that it's as if the output layer was tied directly to your input. It's just not tied directly to your input. It's tied to this kind of weird stretched out representation of your input. Does that help?
Yes, and the weights remain constant, like the neurons in the randomly weighted RNN, the ones that connect to the training layer, does it remain constant? Like the ones that we select and bridge it with the next layer.
Yeah, the weights in this middle layer, the randomly weighted RNN, you draw those once without any you don't look at your input at all. In fact, you could draw them. You might need to know dimensionality of your input. But once you know the dimensionality of the input, you draw this thing once and you don't worry about it. If you have a different type of input later, you can use the same neural network. And these weights do stay constant throughout the training task. And so then you kind of forget, I mean, that this is a neural network at all. You just treat it as some nonlinear filter. And then you only focus on training the weights in this simple thin layer that's near your output. All right, any other questions? All right. Well, anybody who has anything specific about their projects or anything like that, you can come to office hours. I'll flip over to that room here. I'll take a minute or two break in between these, and otherwise I'll stop the recording now. And hope everybody has a good rest of their evening.